All right, so let's get cranking. This quiz is quiz number 1, and it is all about part 1. Remember, there are 4 parts to the class. The first part is all about kind of general setup and general concepts regarding the Internet of Things. So what I'd like to do is walk through the slides really fast and probably spend about 25 to 30 minutes going through as much content as possible related to this first quiz. So let's get started. Remember that part 1 is about the IoT. We're also going to talk about architecture and then setting things up. So there will be questions on the quiz related to all 3 of those parts, if you will, or sections. Certainly the concept of the IoT and what it means and what it isn't, some architectural constructs and so forth that we've been discussing specifically regarding things that we've studied that the Industrial Internet Consortium has made available. And then, of course, some of the coding exercises that you've had to already implement for Lab Module 1 and Lab Module 2. Okay, so remember about the IoT. I've got a nice kind of summary of all this stuff in the preface to my book, Programming the Internet of Things, online through O'Reilly Media. Please check that out if you haven't already, and definitely send me feedback if you have any. There will be an update to that book in just a matter of a day or 2. I had one more follow-up review with my editor, and we've got a really good chunk of content that's going to get pushed up there. First 7 chapters and the new full color cover art. So I'm really excited about that. So definitely check that out. I think you'll find it to be helpful. It will certainly help you with the class as well. So remember that the Internet of Things is a very broad technology area. It's very difficult to narrow down to just a couple of things. It's so broad, in fact, that it makes it very difficult for us as technologists to know how to explain it. So I think it's best to really think about it in terms of not just hype and potential economic impact and so forth, but what it is going to help us solve for business problems. And it really boils down to system integration. System integration is probably the biggest part of the Internet of Things and probably the hardest thing as well. So what you're seeing up on the screen here is a screenshot of a dashboard that I created in a cloud service called Ubidots, which allows you to ingest a bunch of data from your different devices and then report on that data within an online dashboard. You can even trigger events using the MQTT protocol to blast things back down to your device. The protocol, of course, is not a trigger per se, but as you all know, it is a pub sub. MQTT is a pub sub protocol, or publish subscribe. So you can subscribe to events that will get triggered either in the cloud or down at your gateway device. And so what we can have here is some real-time, or I should say, as it occurs interaction. I'm not talking about real time in terms of determinism. I'm talking about real time in terms of streaming data that gets streamed from a device to another system, whether it's cloud or frankly another device. So what are we showing here? A bunch of different screens that represent a bunch of different devices and the data that is coming off of those devices. We call this telemetry. And so keep that in mind. We'll be referring back to this over and over through the semester. Okay, what is this telling us? Notice that there's a drop off here and there's a dead space here. And so all I am pointing out here is that by tracking stuff in a time series manner, we'll actually know when there's either a drop off a ledge or whatnot, and that might help inform what decisions we might want to make as business owners and so forth. So basically, the bottom line is that we care about integration, we care about trends, we care about outcomes. And the Internet of Things, in my mind anyway, is all about managing to better outcomes. By collecting a bunch of data and having it now available to us in time series manner, we can now make better decisions, or we should be able to make better decisions. Okay, now I've boiled this down to 3 kind of core concepts. Measure everything. model what you can to create your baseline and know where your ranges are and bounding boxes and so forth, and then manage to that model so you can basically determine what things are valuable and what things are not valuable. So these three constructs go together and help you to make better decisions, and this ultimately helps us deliver value over just hype and science experiments, which, by the way, science experiments are great for exploring and figuring out what is the right way to bound a problem, but we also need to have it applied to a real business area so that we can actually derive some kind of value from that. And that's, again, how I came up with this measure, model, and manage construct. Okay, but what is really the Internet of Things, and how did we even get here? So let's take a look at a couple of great definitions from Gartner and from McKinsey that I have here and referenced below. And let's take a look at the definition of Internet of Things, which I believe, as I think most folks do, that it was a term coined by Kevin Ashton when he presented an ARFID briefing at Procter & Gamble back in the late 90s. Again, references down below. So I actually like to look at it more in terms of a kind of holistic perspective, where we've got these embedded computing devices that have some kind of ambient knowledge of their surroundings. That is, they interact with the physical world in some way, shape, or form, and then they connect either directly or indirectly to the internet, indirectly through some kind of gateway, or directly in some cases if they support TCP/IP stacks within their systems. Okay, let's consider what devices can do and what services can provide. So I think that when we boil things down in the IoT world, we're really talking about devices, again, that interact with the physical world and provide some means of connectivity to the internet, and those services that provide that value added capability that allows us to take all that data from those devices and actually do something useful with it. Okay, let's take a look at history for just a brief moment. Notice I've got 5 bullets here that kind of frame things in terms of the modern computing era from the 50s all the way to the present, where we had the establishment of modern computing and transistors and Moore's law, etc., moving through infrastructure that was developed to make use of this modern computing technology, and of course, the internet, which was birthed out of the ARPANET back in the late 60s and brought us into the modern world that we have today, with further adoption, efficiencies gained, and of course, scaling by the introduction of software as a service, cloud technology, data center for hire, and now, of course, cloud services and whatnot. Now, we also have very inexpensive computing devices. You can buy a device such as a Raspberry Pi Pico for $4, and that provides pretty substantive microcontroller computing capability. And for $10, you can buy yourself a Raspberry Pi Zero with Wi-Fi and Bluetooth, in fact. And that provides even more general purpose computing capability. So we are at a point now in history where computing is very, very inexpensive, and the access to the services that will provide that value-added business is also very, very inexpensive, relatively speaking. And so now we just have to hook everything together, and that is the hard part. So that's really what this class is all about, is integrating all these different things and making stuff work together in a way that, again, drives business value. Okay, so we notice that looking at history, we've seen a common set of themes emerge. We have tooling that we created to solve a problem. We have standards that we developed to make the tools more consistent and better. And then we have efficiency to scale all of that capability out so we can make more tools and faster and cheaper and so forth and so on. And all of this is just because we wanted a better hammer, right? Well, maybe not, maybe. I'm not really sure exactly, but I do know this, that by applying these constructs here, tooling to solve a problem and establishment of standards so that we can make them more consistent and whatnot, and then gaining more efficiencies by scaling that out, we have the ability to leverage things like the Internet of Things ecosystem, if you will. And so that's a really valuable and powerful construct for us, and that's what we're going to study. Okay, that is it for this one section. Let me blaze ahead to the next section so that we can get into that next part for the quiz. All right, so let's look at architectural tiers. Architectural tiers are very, very important. If we consider our measure, model, manage construct, they fit into this architectural tiering, if you will, not here, but actually here with the edge tier and the cloud tier. Let me go back for just a moment. Notice that we've got a bunch of different things that are going on that represent our measurement, our modeling, and our management capability. When we put these things into architectural tiers, we have an edge tier that basically gives us a conceptual construct to create and run and execute our edge tier devices, things that will interact with the physical world and then provide that gateway to the internet. And then we have our cloud tier, which allows us to leverage all of the services and the scalability capability of the cloud. Now we can take this even further if we want, and we can add a third tier to this, which we'll do momentarily. But for now, let's just consider our 3 M's and see how they fit into this tiered construct where we have measurement at the edge. That's our data collection, our telemetry generation, our modeling, which we actually will manage, or rather have, at both the edge and in the cloud, because we need baselines that will basically be acted upon at the edge. We also need baselines that will be acted upon in the cloud. And then our management construct actually spans both, really, because we are managing to a cloud-based model for edge cases and whatnot that might be relevant within an enterprise or cloud environment. And then we have others that we need to manage to right as close to the devices as possible. Think about a thermostat, for instance. If my thermostat needs to be managed exclusively in the cloud, then I don't have as much control as I would like, since a thermostat should allow me to adjust the temperature as close to the source as possible. But I should also have the ability to track trends and whatnot in a much more scaled manner, so I can actually analyze what those trends are and maybe make better decisions about when I should just instruct the thermostat to basically turn the heat up or down depending on what is anticipated to be the environmental need and so forth. So we've got the on-demand change that would happen close to the edge for both safety purposes as well as direct control. And I've got the analytics capability that's going to run mostly in the cloud, although we can certainly run some of that in our gateway at the edge as well. All right, let's drill down just a bit further. Notice that here we're actually expanding our 2 tiers into components. So we're moving outside of just the concepts and into actual components. And these are the things that you all get to build as part of this class. So what do we have? At the edge tier, we've got 2 things, a constrained device application and a gateway device application. Now, this constrained device application is not designed to just run on embedded microcontrollers that fall within tier 1 or type 0, type 1, and type 2 types of constrained devices as defined by the IETF's RFC 8259. It's really a conceptual concept, if you will, and it's designed so that you can consider running that constrained device application on a truly constrained device. But for our purposes, we're actually going to be running it within our own development environment on our workstation. And so it has a lot more power than we would typically need. The idea, though, is to separate them out so that we can focus a very small amount of ideally high-performing code at the edge within our constrained device and another chunk of high-performing code within a gateway device that will then handle all of the messaging coming from the constrained device app, send instructions to the constrained device app, and then serve as the gateway to the cloud. Now, another thing that's going to be kind of odd for some that may be embedded developers is we're not building the constrained device app in C. We're actually going to write it in Python. Now, there are MicroPython environments that will run within a constrained environment. So some of you may have actually worked with those and so forth. And that's great. And that's kind of the idea here. But again, trying to separate the purposes of this class from what a true constrained device might actually be. And the reality is, though, that the purposes of the constrained device app fit perfectly within the concept of a constrained device. So with that being said, we've got two applications hanging out at the edge. We have our cloud services hanging out in the cloud tier, and that hopefully is self-explanatory by looking at that diagram. Let's expand it even further. Notice that we've got a bunch of stuff that's happening in the cloud. I'm not expanding that right now. We're focusing mostly at the edge tier, but look at all the additional capabilities that the edge tier is actually bringing out. In both the constrained device app or CDA case and the gateway device app or GDA case, we have these comms libraries that allow us to communicate. And again, I'm going to assume that for this class and all the exercises that we'll be building out, that both devices have access to a full TCP/IP stack. Now, in reality, that may not be the case. In fact, we'll study a protocol in class 8 and 9 and even 10 that relies on UDP over IP, but suffice to say that we are expecting an IP-based network to be available using both TCP and UDP at the transport layer. Okay, this next section is about setting up your development environment. I have a separate video on this, so I'm going to blast through this really quickly. So we got GitHub Classroom. You know about that. You should be using it already. If you're not, we need to definitely talk because we're already going into Lab Module 4 as after the quiz on Saturday. So once you're done with that, your DevOps environment is going to look very similar to what you see on the screen right now. You can see that you've got your development workstation talking through your IDE, or rather hosting your IDE, which then talks to your local Git repository, as well as your remote Git repository, which is hosted within the GitHub Classroom environment. It's still part of GitHub, it's just a separate wrapper, and that's how we actually can interact and manage the code and review code and all that stuff. The applications are running within basically a virtualized environment, and many of you have chosen, on my recommendation, to just stand up a Linux-based virtual machine so that it will make some of the work and so forth a little bit more convenient and a little bit easier, especially when we get into the emulator capability, which in fact we'll talk about in Lab Module 4 this Saturday. Here's an optional environment. You can actually try this out if you want. I do need to post some instructions on how to get your Raspberry Pi up and running and configured, and using Jenkins. That will be coming shortly. I actually just need to convert the document. I've already written it, so bear with me. I'll get that posted shortly. Okay, let us look at what we're going to build, and you'll get a better idea of how everything fits together and so forth. So Lab Module Roadmap, we've kind of walked through all this stuff in the past. I'm really quickly going to blast through this right now, as you can see. And of course, the end state is going to look like this on the CDA side, this on the GDA side, and your cloud services or cloud service functions might look like this, although, as I mentioned before, you really don't have to write any code to make your system work within a cloud environment. It really depends on the cloud service provider that you choose. I will walk through some examples of what that looks like within AWS so that you can see how to create a Lambda function or multiple Lambda functions to actually support your IoT solution. Okay, semester project. I'm not going to talk about this right now because we've talked about that already, and I'm going to talk about it more later. Lab Module 1, you should be familiar with this. You should know what code you actually wrote because I will be asking questions about this and understand what your UML should look like. Here's an example right there, and here is your GDA, another example of your UML. Okay, let's blaze ahead to class number 2, architectural considerations and building system performance apps. You'll probably be quizzed on both of these. All right, let's take a look. Architectures. So some architecture definitions provided by Collins English Dictionary are really helpful for us. You can see them here on your screen and see the references down below. I recommend that you know what these definitions are. It's really helpful to understand what an architecture is and frankly, what it's not. They Bottom line, though, is an architecture depicts relationships between different components and even systems and whatnot. We have systems architectures, we have software architectures. Sometimes we combine the two depending on what we're trying to depict and the types of relationships that we need to convey. And with the IoT, this is very, very important because we're often dealing with not just software, but also hardware, as you know. Okay, so why do we need an architecture? Well, let's take a look at a few kind of generic verticals down below. Notice that each one of these, when we think about it, may actually have very common architectural needs, where we've got a source of data and we have a way to convert that data into some other format and then send that data up to a cloud service, analyze that data and make a decision, and maybe turn something on, off, or adjust some device's value or whatnot back at the edge again. This kind of generic use case could certainly apply to every single one of these generic verticals, and so we would have a common architecture to depict them. But we also have ones that are very specific to each one, depending on what we're trying to solve. We also have potentially different governance models, different regulatory requirements, and all kinds of things that actually can impact our architecture. So it's very important to be thinking about what vertical we're in, what industries are in that vertical, and how they actually may need to adopt a slightly different architecture over another one. So with that being said, architectures provide not just a concept or understanding of relationships, but these system design guidelines. And so with these guidelines in place, we can then make better decisions about how we're going to deploy things, how we're going to connect things together, what types of security constructs are going to be required and whatnot, how we're going to manage our components, what types of data do we need to be ingesting or transmitting, and how do we want to transform that data? What about the ontologies that would help us inform how to interpret that data and so forth? And then again, what type of computing capability do we need? And this is not to even go down the path of power and whether I've got to hermetically seal a component's chassis or any of those questions. So an architecture depicting relationships and providing us the system guidelines and whatnot needs to represent all of these characteristics. It's very important that we think about these as we go. We're going to greatly simplify it for the purposes of this class, but I just want to make all of you aware that these are very important concepts to keep in mind. Okay, remember the two-tier architecture diagram that we discussed before, right? Where we've got all of our different components and so forth handling data collection, telemetry, and of course the analytics and so forth that you see in the cloud. Well, we can split this out from 2 into 3 tiers, and this is just a very simple notional example of the different components that might be in one place or another. But notice that within our cloud tier, we can host a whole boatload of different things, including system management or configuration and so forth, orchestration of services that are close to the actual edge. We can split that out. We can have our platform tier running actually potentially in an on-prem data center, which is actually not that uncommon, where we can keep our enterprise tier hosted in the cloud or perhaps even on-prem as well. But the concept here is that we're separating these things out so that we can kind of isolate the command and control functionality within our platform tier and the business use and analytics and so forth in the enterprise tier. That's one example. There are many others to think about. So let's think about why we would do this. Within an industrial Internet of Things context, this might make sense. We'll talk about what the industrial IoT is in just a moment. Platform tier provides the interface between the edge and the enterprise, provides that separation of orchestration and management processing from the business users that are in the enterprise tier. It's an important construct. It's certainly not required for our purposes, so we're going to stay focused on just edge tier and cloud tier and bundle everything outside of the gateway in the internet in the cloud tier and everything at the edge, well, in the edge tier. Okay, now in all of this talking and conceptual discussion and so forth, it really is helpful to have a template which takes our architecture that represents our system boundaries and the relationships between components and maps it into a template which is now a reference architecture. So the Industrial Internet Consortium has a really good definition that I like on reference architectures. You can read that here and see the reference below, but the bottom line is this template provides us a common framework to kind of guide the system development, our software development, and so forth. So it's something that we can apply in many different cases. It's beyond just an architecture. It's actually providing a little bit more detail and so forth, so that when we're trying to create a new design, for instance, we can actually use that template and build our design from that template. Okay, so what is the industrial Internet of Things? So it's a subset of the IoT, just like other, XYZ of IoT are subsets of the IoT. There's the medical Internet of Things. There's the industrial Internet of Things, and the list goes on and on and on. But it really just gives us a kind of baseline, like a separate, or rather takes a portion of the IoT and focuses just on the industrial constructs that are important for an industrial environment. And this could include how we're dealing with industrial control systems, for instance. So I think it's helpful for us to understand this, because this is a big part of probably what you all will be involved in, as you move on from school and go into your co-ops, your internships, and of course your full-time jobs. So I find it helpful to kind of review the Industrial Internet Reference Architecture, also published by the IIC, you can see the reference there, and the Industrial Internet Connectivity Framework, which is a really good way to assess what types of protocols might be helpful and what questions might be useful to ask as you're looking at how to align your own design to the IIRA. And so these are really good questions that you can be asking yourself as you blaze ahead. All right, that is it for now. I think there's just one more thing to talk about, and we will get into design approaches next. All right, so remember, as I mentioned before, we're not actually building an industrial Internet of Things platform. So we're not going to be building out 3 separate tiers, but we will be talking about that and referencing that throughout the semester. I think it's important to understand those because, frankly, this is a critically important part of the industrial Internet of Things, and one that you'll probably encounter. But again, for our purposes, we're going to keep it a little bit more simple and more manageable for the purposes of this class. So let's take a look at a couple of examples. Again, these are just notional, so keep that in mind. Here's one where it shows the gateway device connecting into the cloud. Notice that in this particular case, gateway device can actually have a sensor and an actuator attached to it, because it's providing not only the abilities that we would typically see within a constrained device, but also the gateway connectivity into the cloud. And we'll see this with smart thermostats, for instance, that will certainly have a sensor built in. Here's one where we've got the separation between our constrained device and our gateway device, and of course our cloud hanging out at the top, receiving messages from the gateway device and sending messages back down again. I've isolated these from the color circle standpoint. We've got the blue circle representing the gateway device in both diagrams, and a green circle, which is new, representing the constrained device. Now we can add more constrained devices. So it's the same thing, but more stuff, right? We've got multiple constrained devices all talking to that single gateway device, and which is also talking to the cloud. So no real difference between these two, just as a scaled version of it. Okay, now we have something that we call a mesh. This is where we've got different repeaters in place. Those are highlighted in orange, and will provide the ability for one constrained device to pass its messages through another constrained device into our gateway device. And we'll actually talk about some of the protocols that are useful for this purpose in part 2, but that's not part of this quiz, so you don't have to worry about that right now. But there are protocols that are designed to allow that type of mesh networking and so forth, which provides very convenience for us when we're trying to lay out a design for a system. And so we can leverage the protocols and whatnot that have already been developed and are already available for research purposes and for implementation purposes and so forth to help solve this particular problem. Or you can implement it in software as well and use protocols like just TCP/IP over Wi-Fi to facilitate that, although not really necessary when we're dealing with a Wi-Fi type of network, but it is one that might apply if we've got repeaters for that Wi-Fi network. Okay, what about this? Now this one's a little bit different. We don't have repeaters in place, but we do have this thing called a bridge, or a data bus broker, if you would, a data broker. And so this allows us to communicate between different data buses, right? And we talked a little bit about that. This is PubSub at its heart and soul, and you can see how that is being implemented or rendered rather by that kind of red circle device and so forth. Then we've got another one, gateway device, encircled in blue, so you can kind of see that they're doing the same type of job, but they're in different layers of that layered data bus architecture. Okay, so I talked about where the complexity lies within the IoT. It's mostly about the integration, and most of the integration challenges happen at the edge because that's where we have a lot of heterogeneity and so forth. Now, certainly that's not where all the complexity lies with IoT, but is where a big part of the complexity calculus will actually hit us. So this is something that we need to be cognizant of all the time when we're thinking about our different devices and so forth. Okay, let's take a quick look at what it might look like within a cloud environment. You can see here that we've got let's see here. We've got a bunch of different devices that talk through a gateway, a router, and then blast their messages up to one of many different cloud services. We'll talk about those 4 cloud services when we get into class number 11. Here's a target reference architecture, including a little bit of DevOps, not a lot, but a tiny amount, just from a conceptual standpoint, so you can see how everything fits together from a systems view perspective. We talked about the software view. This is the systems view. Again, it's not designed to represent a specific type of diagramming approach or whatnot. This is just really just trying to make it as simple as possible. Part 1 is going to be focused on this part here. So this is what the quiz is going to be about, and you can see all of that information below. Part 2 is going to be focused mostly at the edge, and we're going to continue our conversation on the edge during our class on Saturday. Part 3 is going to take us into the gateway and start to touch on the cloud, provide some connectivity capabilities and so forth. And then finally, we're going to get into the cloud here with part 4 and focus most of our time and energies there, though we'll dabble back in part 3 and part 2 again as needed. All right, that is it, folks. I think, oh, I got one more. Basic system monitoring. I should probably cover this. Let me get into this really quickly. All right, so let's take a simple smart home scenario. We're gonna actually call this the RAT, or remote and auto adjust home temperature. So we're gonna actually break it down into what the product name is, just because we can create a name and it's kind of fun. We're gonna identify our key objectives, what problems we're trying to solve, who our end users are, what the system boundaries are that represent the target design, and of course our system relationships and so forth. And you can see on the right hand side, this is where our architecture and our reference architecture will come into play. So this diagram looks really similar because we've talked about it at length. And this is where we've got our constraint device that can receive inputs from different sensors, and it can talk to an actuator to trigger a type of activation. And of course it communicates with our gateway device, which also talks to the cloud. You can see that we've called out these capabilities on the right hand side of the screen. And I further mapped out the different subtasks. So as you can see, we start walking through this kind of simple use case, and then we start breaking it down into like the different, components and users who might be involved. We map out a simple architecture and start talking about what components belong where and how they interact and so forth. And then we break it down into further subtasks. We can take this and then we can actually extrapolate developer user stories that will help us to actually build the solution and test it, validate it, integrate it, and of course, push it into production. All right, I think now we're done. So this is Lab Module 2. We're not going to go through this, but you should be familiar with the code that you wrote for Lab Module 2. I will be referencing it during the quiz. And I think, here you go, your diagram for Lab Module 2, your UML for Lab Module 2, gateway device, your UML for the gateway device. All right. And then we are done.